right, next up we have Alex. Thanks, Alex.
All right, Alex Mykyta, talking about PeakRDL today. Quick show of hands, who's already used PeakRDL or is aware of it? Yes, okay, awesome. So this will be a lot of review, but for those of you that this is new to, I'm gonna teach you a little bit about it. So what is PeakRDL? So first of all, I'm gonna start with what is CSR automation? So CSR, what I'm referring to is control status registers. So these are typically, not to be confused with control status registers that are inside your CPU. These are memory mapped peripherals, typically visible via an interconnect, NOC, maybe remotely through PCIe or local CPU. It's your hardware-software interface. Now, what is CSR automation? It's this idea that you have a single source of truth in some machine-readable format. And that's what we're going to call the specification. And from that, it is convenient to describe your register space and generate a bunch of things. So that could be your RTL implementation. That could be test models, whether it's UVM or some kind of Python base for CocoaDB or whatever. Eventually, you're going to need some header files for your software team to consume. And IPExact is a great way to pass on information for other vendors. And then lastly, of course, documentation. So that's kind of the gold standard of what we want for CSR automation is you kind of have one source of truth. So you step back and say, that sounds great. I want to highlight that each of these things are not difficult things to solve. You can hand code all of this stuff. This is not a monumentally difficult thing to do. It's just tedious and it's boring. You want to be focusing on your actual design, not CSRs, because they're boring. So great, we want to do that. I'm going to tell you a little bit of a story, and hopefully you'll find this a little bit relatable, because you might have seen something similar in your workplace. So great, we want to do this. So I've kind of not totally have experienced this as well. I'm like, okay, well, I want to design some CSR as automation. What should my specification be? So we want to invent something that is machine readable, human friendly, fully encompasses our register maps. So we can explore a few different options. So it can be tabular. We could have like a CSV or Excel sheet. That's pretty natural, it makes sense. It's a little hard to describe hierarchy. And what I mean by that is nesting subsystems, or like a classic example is like a DMA controller that might have multiple channels, and you might need to have a repeating structure like that. So that's a little hierarchical, not just registers and fields, but also like sub concepts. Word doc, that's a clever idea. Okay, we can have our code be our documentation, and then we don't have to write documentation, right? Okay, but good luck with Git. Okay, we can do something more structural. XML is evil. JSON is a little bit better. YAML, okay, that's a little more human-friendly. That's kind of nice. We have some nice libraries to read that. But eventually what you end up realizing is these are all very schema-laden solutions. We really want to have block-level reuse. We want to have to be able to parameterize things. And sure, I can code that into a YAML schema and make it kind of work. And it ends up being a little icky after a while. And so I kind of went through this journey in my head at one point. And this XKCD comic also started nagging me and taunting me. Made me really uncomfortable. And the numbers here are a little different. And the reality, there's maybe 2 competing standards and like 50 other implementations of random things. So but the concept is similar. Fortunately, we have an existing standard that is pretty decent, SystemRDL by Accelera. And I'll give you a little quick tour on what this looks like. So this is just a quick view of what it looks like. You can kind of see some structures. We have some fields, we have registers, and it's wrapped in this thing called an address map, adder map. We have addresses and stuff like that. I'll show you a few other things. We have some modularity, great. So we have lines 1 through 3, a FOSSI device. We instantiate it 3 times at 3 different address offsets, give it device A, B, and C. And hey, look at line 16, we can make it an array of them, an array of 16 of them. So here's kind of the highlighting. We have type names, instance names, address offsets, and also there's on the bottom the hex 100. That's the stride of an array. We can also do multidimensional arrays. And hey, it's parameterizable. So I can create those modular reusable blocks and make them a little bit more generic. So we have Fossey device. Maybe we want to have it have 4 channels by default. Great. We have an array of write channel, read channel. Great. And then down there on line 14, you can see I'm overriding it, saying, oh, you know what? I want to have a second device, device B, which is 16 channels, and that's at a different address offset. So you can start seeing how this becomes useful. Now, OK, well, let's step back. How do we actually describe all these behavioral things? SystemRDL has a whole slew of properties that you can assign to things. I'm not going to go over all of these, but just know that they exist. And there's probably millions of permutations of these that you could describe something. So let's do some examples. So here's the 3 different fields. Think of your software fields and how you'd ever interact with them. So the first one is a pretty straightforward. This would be like a control register. So software can read it, can write it. The value is visible to hardware, so hardware can read it. And if you think about that for a second or two, you realize, oh, well, that actually infers a storage element. Great. OK, now we have a register in our register file. The next one down is a read-only field. So software can read it, hardware can write it. Think about it. There is no storage element. That's just a wire. That's a wire that gets memory mapped. Last one, there's a kind of a volatile field. Software and hardware can read and write it. And then in order to control kind of who does what when, on line 20, we have that write enable. So that infers a write enable strobe. So great. OK, we can start building stuff. You can do kind of fancier things. So here's a few here's some other fancier examples. You can describe a counter. Counters are really useful. We have them all over the place in our code to keep track of stats. So the first one is an up counter. Software can read it. It infers an increment enable. So you get on the hardware side, you get a wire, say, OK, strobe this to increment. The next one, we can do something a little more clever. We can say, oh, this is an up-down counter that we can either increment or decrement. And not only that, we can increment by 3 and decrement by 2. I don't know why you'd want to do that, but you can. And then the last one, this is a little bit different. Say we want to do like a sticky bit. So we want to log an event and say, well, OK, we want software to be able to see it when this happens. So software can read it. Hardware doesn't need access to it. But hardware does get a wire to say, hey, if you strobe this, then it sets the value to 1. And then on read, when software reads it, we want it to clear. And then if both of those things happen at the same time, we want to be explicit on which one wins. So great. So now you can do some really cool things, because now that you have these concepts that you can individually build, we can now actually put this together. So that counter that I declared before, I'm going to instantiate it 3 times. I'm going to give it a bit width, each of them 32-bit. So we have 3 32-bit counters, and maybe this is a packet, byte, and error counter. I've instantiated them at different address offsets. And well, it'd be really nice to clear them, because software, we want to atomically clear them in one operation. So we give it a control register and say, OK, you know what, so software can write it. So that's line 64. Line 65, hardware, we don't need any access. 66 is fun, because you can say, OK, we're going to write a 1 to this, and then it'll automatically clear itself. So it's a single pulse. And then the neat thing is line 70 through 72, we now connect them. So whenever the control clear stats gets asserted, those counters get cleared. Great. Remember, I'm not doing anything earth-shattering here. I've made 3 counters that can be cleared. Anyone could code this up in your sleep. But the thing that's really valuable and powerful is this is now in your spec. This can now be described not just to generate your hardware, which is not super impressive. I mean, look at it. It's 3 counters. But you can now have this carry over into your documentation, into your modeling code, into your C, all sorts of different output products. So perfect. This is really cool. This is what we're looking for. That was my experience. I was like, aha, this is it. But we have a little bit of a problem. This is SystemRDL 2.0 came out around 2018, and that's around when I kind of started getting interested in it. At the time, all the existing implementations of RDL2 were closed source. There was an existing open register design tool by Juniper that is really neat, limited to 1.0. Useful, but not what I was looking for. And then the other problem is I have no clue how to make a compiler. So cool. OK, yet. So I decided to get my hands dirty, and I started learning about lexers and parsers. This was a kind of excuse. That is me. And it was like, whoa, this is kind of fun. And actually, wait, this is actually doable. So fast forward, I have a minimum viable product, and I publish it to PyPy. And I'm thinking, okay, this is a silly thing. No one's going to use this. And then, we got a few issues and pull requests. And people are telling me, oh, you got to fix this. I want to do this. Give me this feature. And download counts are going up. And I'm like, oh, I think I must have struck a nerve. Because after kind of looking at the chatter on the internet, I realized there was definitely some demand that I didn't understand yet. And this kind of formed my guiding principles for what came next. Because despite there being loads and loads of existing open source tools that do this, and also commercial tools that you can pay for, they have like enterprise support and everything, for some reason people are still building their own. And I was really baffled by that initially, but then I realized, well, wait, I'm the one doing that too. So clearly I can answer my own questions. And these are my guiding principles. So designers are ultimately still going to want to build their own tooling. And that's basically because for register automation, ownership and authority over it is actually really important. You're always going to have to do that one weird custom thing that no one else supports, and that's fine. The other thing is access to a decent language like SystemRDL, rather than making up your own scheme, is actually really empowering. And not only that, it's a standalone compiler that you now have an API that you can use. So that's really interesting too. So on top of that, that was like, okay, well, I need to make really good documentation because that kind of matches with these principles. So great. So now I have a compiler, and now I want to kind of follow those principles. So what comes next is PeakRDL, open source CSR toolchain. You can pip install it like that. I hacked together a little logo. I'm not a graphic designer, but there you go. So what is PeakRDL? Primarily, it's a command line control status register automation framework and toolchain. That's kind of how I'll advertise it. It is extraordinarily plugin centric. Just to kind of give you a tour of this diagram, you basically, one or more RDL files go in on the left-hand side. They go into the compiler. They get parsed, compiled, elaborated into kind of a tree-like data structure. Things get validated, and then on the right-hand side, you have that kind of green icon, and that's our model that we can now draw from. So we now have these two boxes here with importer and exporter. Okay, great. Importer is useful because I can now pull in foreign formats. So maybe you had that old Excel sheet that you were like, you know what, we really like PeakRDL, but we want to build a converter for that, so you could. And then exporters, you can generate stuff. That's not enough, obviously, so I started building some tooling to plug into this so we can take in IPExact, so maybe some third-party vendor gave us an IPExact file. And then we can also generate all these other things, so RTL, UVM, HTML. I'll talk about these in a second a little bit more. So great, let's take a look at some of the things that we have available today, ready to go. There's the reg block generator. This is, you generate synthesizable RTL. We can, that's generally the structure. We can, the first iteration of it generated SystemVerilog. Just last week, I had a community member reach out to me, say, hey, I ported this to VHDL. I'm like, oh, wow, every single feature. It's like, yeah, fully tested and everything. So we actually have both languages now. You can do a lot of a variety of bus interfaces, so APB, AXI, Avalon's a new one that I added. And you can also just add a plugin, say, hey, I have this internal protocol that we use in our organization. Like, you can just add that, and it'll just glue right in, and everything else works the same. All the cool little features that I described earlier in the RDL language are essentially all of them are supported here. Another one that gets people excited is the HTML documentation. So you can take that RDL description, or maybe a mix of RDL and XML or other formats, put it through the grinder, and then out comes some dynamic HTML, and you can you can see it preserves the hierarchy. You can play with fields, you can fiddle with numbers, you can explore it really dynamically, and it has a really great search feature that you can basically find anything by name through either in description or identifiers. So really useful. People were thrilled about this when I first put this together. One thing that's new about this a year ago, I have a C header generator finally. So if you want to take your RDL that's on the left-hand side and convert it to a C header that you can now overlay onto, cast a pointer to it, you have this struct overlay. Bit fields are optional. That's contended whether that's a good idea or not, but that's available if you want. But then there's also these define macros that you can use to kind of bit bang things if you need to. And then there's a few other ones. So IP exact I talked about, you can import, export that. If you are migrating from a different format, you can convert things to SystemRDL. And then, of course, I mentioned UVM. That'll generate that UVM register model. So great. I want to take a minute and actually show how you extend PeakRDL, because I think that's the thing that I really am proud of in this toolchain is it's really easy to go and just say, hey, you know what, I have this really weird thing that I need to generate. How do I do that? So this is how you can do that. In Python, you basically extend a class to an exporter plugin. We give it a short description. On line 9, we add an argument, say we want to do a prefix. The goal that we want to do here is we want to create a Verilog include. Each has a define with an address. That's maybe the hypothetical example here. So add an argument, we prefix that macro. And then on the export side, so lines 11 through 18, pretty straightforward. We open a file. Next line down, we iterate through all of the registers. If there's arrays, we unroll them. And then if it is a register, because that's the only thing we care about right now, we generate a macro name, so we get the full path. And then we write it to the file, and that's it. So for PeakRDL, extending it's super easy. You basically just point it to where your thing is. There's this other configuration mechanism that you can point it to where your Python files are. You say, OK, this is how you import it. And then, hey, look at that. It exists. So if I do PeakRDL help, there it is, FOSSI exporter right on the bottom. That's what we just defined. And it works. So I have my turbo encabulator example. We fed that in, gave it a prefix of yay, and then out, VH. There we go. We got all of our addresses in a bunch of defines. So you can see that's super quick to do. This example maybe took me 10 minutes to put together. Because it's so easy, past few years have been really exciting because a lot of people have been building stuff for PeakRDL. A few call-outs. There's a PSS exporter that Matthew will be talking about hopefully tomorrow. On the next page, there's, let's see, we have an OpenTitan importer exporter to handle their HJSON format. And then there's that VHDL data source and put together, and that's been really exciting to see. So wrapping up, there's a few other updates that I'd just like to share of new things if you're already familiar with the tooling and future plans. So one thing that I pushed out just last week, if you're a fan of using Sphinx docs for documentation, there is now very nicely natively integrated plugins for PeakRDL. So you can basically point Sphinx to your RDL files, XML files, and whatnot. It'll read them in. It'll embed that dynamic HTML into your document, and then you can now cross-reference things. So, inline, that's restructured text right there. You can, reference nodes in your design, and then it'll render nicely to clickable links that'll take you directly to those references. So really great for like user guides or programming guides for software people to consume. The other thing you can do is you can do inline documentation. So if you're interested in actually putting the description or the contents of your stuff in your document, you can say, hey, I want to document this one node. I want that control register to be in my document. So that'll get sucked in, and then it gets generated right inline in your restructured text. This is a nice pathway to now export into other formats. So if you wanted, so Sphinx, if you're not familiar, that can generate other things like PDF, EPUBs if you wanted to do that, and a slew of different formats. So structurally, this path now exists, and now you could make like a nice product document in a PDF form that you can email to someone. So great. A few more things that I've added that are kind of nifty, and also just things to be aware of. Python 3.6 I'm dropping pretty much wholesale. That's been end of life for a while now. Generally, this is going to track with whatever GitHub Actions makes it convenient for me to support. I love supporting the old stuff, but it gets annoying after a while. The other thing is that I'm kind of really happy with is the static type hints in the Python APIs. Made those a lot better now that I don't have to deal with 3.6. So if you've ever used like the get property, that was just like a string you put in. Now you actually get proper autocomplete. And also you get proper type annotation on the bottom. So if you're using like Pylance or something in Visual Studio Code, you'll see those little like gray hints kind of on the left-hand side of like what the type should be. Notably, the reset one always bites me because you think, oh, a reset value of a field, that's always an integer, right? Well, no, in RDL, you can technically have it be a reference to another field or some signal or something like that. So that can be a little confusing, or that'll be a bug report coming into your inbox eventually if you don't fix that. So really useful to know that. Lastly, some future plans for PeakRDL. These are some things like one thing I actually really wanted to get done this week, but didn't get the time to finish it, was a proper bus decoder generator. This would not be a full-up interconnect, but basically if you wanted to have a more hierarchical design, you could say, okay, we have a decode node that branches out to different devices and have that be interface agnostic, make it either work for AXI Lite or APB or AHB or any other bus interface like that. The HTML documentation generator, I want to overhaul that. It's been working great, but there's some features that I'd like to add. One thing is scaling for large designs, cross-references, and then I think I have a path forward to make it fully offline and not require a server side. It is still a statically generated site, but there's still some annoying things about that. UVM exporter, generally just wanted to rewrite it for extensibility. And then I have some planning in place for kind of doing a version 2 of the compiler. There's a lot of features in my backlog, and there's some performance updates that I would like to get to, and that might require pulling some stuff into a compiled language rather than Python. Either way, the API, I think it's important for accessibility reasons, it has to be Python, because that's what a lot of people know. Lastly, I'd love to get involved in the Accelera committee to maybe see if I can get a RDL 2.1 out there or something like that with their authoritative cooperation. So great. Thank you so much. I want to thank all the community members already out there that have been building stuff and helping with like bug reports and everything like that. I would not be able to have built this alone, so really appreciate that a lot. Thank you.
Nice work. Great to get like a follow-up talk from the earlier SystemRDL talk
you.
a couple of years ago. We have questions. Okay, Hugo.
Hello. Thank you. I've heard, we don't use it at low risk, but I've heard a lot of people at other companies using it and really enjoying it. I have played with it. I played with the OpenTitan converter with some of the OpenTitan blocks, which leads me to my question. How easy is it to extend the SystemRDL language? For example, in OpenTitan, we have shadow registers which need to be written twice. Is there kind of an attribute system in the SystemRDL language?
Yeah, so there's a RDL, the language itself has a thing called user-defined properties. And you can, I had that whole table of properties that are kind of the built-in ones. Oh boy, here we go. You can go ahead and define additional ones and basically extend stuff. The register block generator, for example, I do have a mechanism of buffered reads and buffered writes. So say you have multiple registers that need to be sampled atomically. You could have like a trigger, maybe that's like some event that triggers and latches everything, and you can read them all. That's described by a user-defined property. That's kind of an optional add-on. It really is, you can extend it to whatever you want via these properties, and then you just kind of add to the namespace.
Amazing. Thank you very much.
Cool.
I have kind of a silly question. So I noticed that you were showing off the markup file that you were using. Do you have a VS Code extension for that?
Yeah, actually. Oh no.
Yeah,
that's a VS Code extension to do syntax highlighting that I also put together.
Oh,
so
awesome.
You can just pull that from the marketplace.
Okay, I'll talk to you afterwards.
Cool.
One question from my side. So you said you were interested in kind of a SystemRDL 2.1 or something like that. So what features are you missing, or kind of what's the thing that would you you would want in a 2.1?
Sure. I think there's two answers to that. If you look at the existing spec, there's a few typos or just clarifications that ought to be in the spec itself that unfortunately generate a lot of questions on my end. I've been able to work with committee members to clarify them and at least have my understanding be aligned with what the intent was. But getting that feedback back into an authoritative document I think is important. Beyond that, yeah, there are a few features that I think would be interesting. I can't think of them off the top of my head. But yeah, a lot of it's mostly just clarifications just to keep it a little tidier and avoid those silly questions that I get sometimes.
You mentioned that some of the work next up is going to be on the documentation system, just on the kind of what's next slide at the end. Can you talk a little bit more about what you would want to do there?
Yes. So one thing that for the first one, that there's cross-references. Right now, your description strings are something that get parsed, and as a bonus, I process that as Markdown. There's no clean mechanism to say, oh, I want to, in my documentation string, refer to a different node in my tree. Because sometimes, if you're talking about one register, you might be talking about something else in your design as well. So cross-references there. Scaling, the documentation reader and search and everything works decently well up to about 100,000 nodes. After that, it gets a little bit slower, so I want to make my indexing better and also put a lot more information in an unrendered format and then render it client-side. That'll speed things up and keep the footprint down on your disk. And then lastly, the fully offline support. Because I dynamically load things in that HTML generator, there's nothing server-side happening other than hosting the page, but there's core security features on most browsers that are enabled that prevent you from doing that in an offline state. So there's a loophole that we can get around that.
Okay, awesome. Any more questions for Alex? Yes.
I have maybe a little weird / personal of a question, just with regard to has there been adoption within your company? Because I was previously at a large chip company that was integrating a lot of really cool PeakRDL stuff, and it was a great experience. Have you experienced the same in large SoC projects that you guys work on?
Yeah. No, this has been integral in my workplace. We use it all the time. I've also heard about other companies adopting it. Just through GitHub issues, you can kind of infer who's working where and figure out where they're using it. So it's been neat to see. Some of this stuff I know either through colleagues or internally has been silicon proven. So yes, it's being used for sure.
Thank you. Cool. Great news. Okay. Thanks again, Alex. Appreciate it.
Thank you.
Cheers.